We're going to create some more compounds. We're going to also name them as well. So we're going to go through, and from the periodic table we're going to take a look at magnesium and bromine on the periodic table. Magnesium is a metal with a +2 charge. Chlorine or bromine is a 1- charge on the right side of the periodic table. So we're going to combine these together. We have 2+ charges from magnesium. We need to have bromine, each of them with a -1 charge. We need 2 of them to balance out the molecule. The name of this overall is just called magnesium bromide. And the reason for this is because we have defined charges on these. If I say I have magnesium on the periodic table, I know that it's a group 2, so it has a +2 charge. I know that bromine is in group 7, so it wants to gain 1 electron. If it's in an ionic compound, it'll be a -1 charge. So that's how this goes. If I want to deal with phosphorus and chlorine, I look up the periodic table, count the number of valence electrons. I note that they're both on the right side, so they're non-metals. They're going to form a covalent compound. Phosphorus is in group 5, chlorine is in group 7. So they each have 5 valence electrons for phosphorus and 7 valence electrons for chlorine. If I were to form a compound out of that, I'm going to require 3 chlorine molecules, or atoms, in order to combine together. And I can form the bonds with these. So now if I redraw this as phosphorus, the 3 chlorines, and the 2 valence electrons, I must show all of the electrons if this is a proper electron dot diagram. So the name of this we would come up with is, this is a phosphorus molecule with 3 chlorines. It's the more electronegative atom, so it would be phosphorus, and there's 3 of them, trichloride, so phosphorus trichloride. So for making a compound with oxygen and copper, it's a little more difficult. In the first 2, we knew either how many valence electrons were available, or in the or what group they were in, so we knew exactly the defined amount of valence electrons, whether the charge was going to be a positive or a negative, and what that charge would be. Oxygen falls into that realm, but copper, if you look it up on the periodic table, actually has 2 different oxidation states. One is a +1 and one is a +2. And until we're told what that is, we actually don't know what the charge is. So we're going to try something a little different here. I'm going to define 2 compounds for you already. One is CuO and the other is Cu2O. And we're going to go through determining the oxidation states of the various atoms on it, and we're going to name this compound. So for copper, we know that the oxygen attached to it has a 2- charge in both cases. We need a compound that's electrically neutral, so in this case I only have 1 copper, and therefore on the other side I have to have a copper that has a 2+. They have to be electrically neutral. For the second compound, again I have a 2- charge on it, but now I've got 2 coppers, and the 2 coppers in total have to add up to -2. So each one of the coppers is going to have a +1 charge on it. So now we have to find out different ways of naming it. And the first one is just using the name copper, so the actual metal's name, and in brackets we're going to put Roman numerals, the charge of the metal. So in this case it was +2, and we're going to use the Roman numeral 2. And the final word is oxide. So it is the 2- oxygen. For the second compound, again, we're going to call it copper, but we're going to use a 1+ charge because there are 2 atoms of copper, but each copper atom only has a +1 charge, so it's copper 1 oxide. And that can help us define the names of these compounds. There is another way to name this. So knowing that copper has a +1 charge and a +2 charge, we can use the common name for it, which is cuprum. And now we have to relate it to the oxidation state. If it's a lower oxidation state, we put the suffix OUS on, and if it is a +2 or the higher oxidation state, we put ic at the end. So this gives us cupris and cupric, depending on the oxidation state. So for the first compound, we see the copper has a +2 oxidation state. That's telling us that it follows this one, and the name of this then is going to be cupric oxide. There's no need to put the Roman numerals in now because the cupric is defined as the higher oxidation state of the two. In the second example, we have copper with a +1 oxidation state. So we're going to define this as cuprous oxide. And there's no need to put in a Roman numeral for this, as this is already defined for us as well.